Greetings, 460 students. I am somewhat convinced that talking to a number of you guys about the Trammel Blaze, about writing the assembly code, about integrating it into your design, a good number of you are just utilizing what I gave you as far as the test bench, the instantiation, even the assembly code to implement your first project where we replace the counter with the processor. What I want to do is take a little bit of time, take you back to my favorite author, to my favorite book, to Pong Chu, and let you listen to me read Pong Chu to you through a few of his chapters where he talks about the Pico Blaze. So I'm going to jump to page 402 and I'm going to go to a full screen mode. And now we're going to walk through Pong Chu's write-up with a few of my notes documenting some of the changes. I highly recommend that you have your textbook out and you make notes as we go through it. If you do not have a hard copy of the Pong Chu book, I can't recommend you getting it enough. I think the end of your semester, those of you that have got to know Pong Chu, have worked through his book, learned how to read it, will be successful without a doubt. So the first thing is he gives you an overview of the Pico Blaze. And so what I want to point out is that now we've got the Trammel Blaze, which is an emulator of the Pico Blaze. So I have implemented the processor using the Pico Blaze instruction set architecture. Most of the comments that Pong Chu makes regarding the Pico Blaze applies to the Trammel Blaze. The difference is now we have a 16-bit architecture. Now he talks a little bit here about how much space within the FPGA the Pico Blaze takes. I have not got to that point with the Trammel Blaze yet, so that'll be a future discussion. So he opens up his discussion basically providing a case for why you want to use an embedded processor. Up to this point in time, you've learned about state machines and learned how to utilize a state machine essentially as a controller. Basically, with a state machine, it's your custom design. You can provide a lot of different operations. But once you move to a microcontroller, you have a much more flexible tool at your fingertips to support the design of your FPGA. And that's his discussion here. It's basically building the case. He documents basically the transition from a state machine to an embedded processor. And the architecture, if you've taken 440 down below, begins to take shape. Computer architectures, for the most part, in this level of architecture, are all about the same. Instruction memory, program counter, decode, registers, ALU, many things are very similar. So what you have at the bottom is the architecture or organization of the Pico Blaze. What I wanted to do on the next page is itemize how that changes with the Trammel Blaze. So in the Pico Blaze, the data path through the machine is 8 bits wide. That means the internal memory is 8 bits wide. The ALU provides operations on 8 bits of data. Whenever you input or output from the Pico Blaze, it's only 8 bits. And it turns out it's a little limiting when we try and do some of our later projects. For the UART, 8 bits is fine. But as we move, 16 bits becomes a little easier. So the redesign has 16-bit data width, 16-bit ALU, carrying 0 flags, a 16 register 16 16-bit internal registers R0 through RF, We now have 512 by 16 data memory called the scratchpad memory inside of the processor. In his architecture, he had one 18-bit instruction, which recall it was an 8-bit architecture that allowed him to have one instruction per word. For myself, the implementation I chose is I have a 16-bit instruction. What that means is if I need immediate data, I'm going to need a second word to the instruction. In the Pico Blaze, you had 1K instructions. Now we have 4K instructions. We have a 128 word call return stack inside the machine. And if you wanted to use it to the max, you have 2 to the 16th output ports, 2 to the 16th input ports. All of the operations on the I/O are the same, 2 clocks. We're going to see more about that later. So, top level of the processor is the processor itself and the instruction memory. We call this Trammel Blaze, we call this TB underscore ROM. This is now instantiated in Trammel Blaze underscore top. What you need to do is you need to generate the memory for the instruction memory. Turns out you also have to generate the memory for the scratchpad memory, which is just 1K single port RAM. Top level HDL models are the same. All the ports are the same, except for we've added the I/O enable. The only difference is the data path on the port ID input and output port is now 16 as opposed to 8 bits. The development flow is very interesting. On the next page, we're going to look at it. You're going to see it's very similar to the SoC flow. So we're really not reinventing any wheels, but we need a method to our madness. So let's go look at that flow for a second. The flow is very similar to what we've seen where you come up at the beginning, you have to partition between hardware and software. Each then has its own path. This discussion will cover both paths. It'll talk about the hardware side, it'll talk about the software side. What I've highlighted in red in step 7, I cannot emphasize enough. There are still some of you who are attempting to go from design to implementation. You're going to waste hours. And you have a very low probability as we move through the semester of achieving your goals. So please, everybody, write a test bench. We covered it in 360, how to write test benches. Up to this point in time through the project where we just replaced the counter with a processor, very simple. It's going to get a little bit more complicated once we move to the receive engine of the UART. So the instruction set is exactly the same. So we have logical operations, arithmetic operations, compare and test, shift, rotate, data movement, program flow, and we're going to take a peek at these as we go through. So the programming model is we have internal registers. In his documentation and in the PicoBlaze documentation, he refers to the registers or the operands as S, X, S, Y. In my assembler, they're referred to as RX, RY. Program counter, top of stack. So most of that is happening behind the scenes. KK is the constant for your operations. SS is a memory location that you're referring to inside of the scratchpad memory, and then AA is an external is the address for jumping inside. So the format is very simple. Operation, register 1, register 2. Operation, register 1, constant value. Operation, register. So he refers to these register format, register constant format, single register format, or there's an operation with just an address, which would be like jump to 1, 2, 3, 4. And then there's some operations like enable interrupt, disable interrupts that have no operands. So we all should be comfortable. All these instructions are very simple. The behavior is documented very well. In this case, it's an and. He doesn't cover the zero flag here, but the 0 bit will be set. So you can AND two registers. You can AND a register contents with a constant value. We'll use that when we're masking data looking for particular bits in a status word that we read. Or exclusive OR. Now, one comment about the exclusive OR that's good to know is that there's no NOT or no invert instruction. So to perform this operation, all you have to do is exclusive OR the register that you want to complement all the bits with FFFF, and the end result will be the contents of that register are complemented. In the arithmetic operations, what I've done is I've crossed out the alternate representations of the opcode. On the left are the opcodes that I've implemented. And basically it's just showing that you can do adds, you can do an add with carry, subtract with carry, and this allows you to deal with values that will exceed the 16-bit range of our architecture. Compare, please note that it's the COMP instruction. In essence, recall compare does a subtraction. It doesn't modify any of the registers, but the subtraction will then set the flags that you can then make your logical jump based upon. The test instructions, the shift and rotate. So there's a shift left 0, so that shifts left, 0 fill, MSB goes into the carry bit. For us, this is a 16-bit register, so it's bit 15 that goes into the carry, and so on. Shift right, 0 fill, shift right, 1 fill, shift left, 1 fill, shift left, X, and what we're doing is preserving the LSB. Shift right X, again shifting, preserving the MSB. Shift left all, which is basically shifting through the carry bit back around to the 0 bit. Shift right all, again. Rotate left, we're rotating the 16 bits in our register with the MSB getting dropped into the carry bit. Rotate right, same thing with the LSB getting dropped into the carry bit. Data movement instructions, you can load registers, fetch and store between the internal memory inside of the Trammel Blaze, input and output where we're interfacing to the other logic that we've added to our design to interface with the Pico Blaze. So we have load instructions, store instructions, input and output. For program flow control, we can jump directly to an address. The terminology that I've used is a little different. It was easier for me to parse the code if I had just a single word instruction. So jump, if carry is jump C, jump not carry, NC, jump if 0 is set, Z, jump if 0 is not set, jump NZ. And these are just changing the flow of control by jumping to a destination address. And the diagram shows a subroutine call. Down below we have the calls. The call instruction is used in conjunction with the return instruction. So when you want to write a subroutine, you begin it with a label that you'll reference when you perform the call instruction. And at the end of the subroutine, you have a return instruction which sends you back to the instruction after the call. And again, we can have conditional calls, not carry, zero, not zero. We can always return, which is the return of carry is set, return of carry is not set, return of zero is set, return of zero is not set. Then there's instructions that deal with interrupts. We've seen that there's a certain manner that we handle interrupts, and we'll talk about it later. It's particular here, the return from an interrupt, but this time we're returning, we want our interrupts to be disabled. Or here we're returning from an interrupt and we want our interrupts to be enabled again. At the beginning of the code or at the point in time where you want to enable the interrupts, you execute the enable interrupt instruction. If at any point in time you want to disable the interrupt, you execute the disable interrupt instruction. For similar directives, I took a little bit of a different change. I combined the reg and the constant constructs to just have an equate. So with my equate, I have a label, the keyword EQU, followed by a substitution string. If the substitution string is R0 through RF, it will then substitute for a register. If it's anything else, it'll treat it as a label and we'll expect to find a label somewhere in your code. That may not be exactly right. It'll just substitute for the value that's here. We're not worrying about those guys. So I'm going to stop. I'll pick up the next one on chapter 16, but that is it for this guy.